here with you. We reached our last unit here. This is 12. And this of unit 12 over Kinetics, which is the speed or rate at which we are. The board behind me is these are the in school all this time. Again, these two now are now no. So you'll always be referring to and modified house and calendar. We now remember both in, linked home. I believe him too that I'm not sure that we would get this kind of seeing as how the rest of the semester plays out. Either way, though, this will be available all students or not, because it is important and to pick your next class stream, whether that be here at Harrison or as your first history class in college. I'm here. There. Okay. 12 1 chemical kinetics. So again, kinetics is very concerned at which reactions are determined by collision, the rate, force reaction, particles collide. So the speed at which collide and strength with which they will determine that. If you get back and know a long August 2019 started off with a little overreaction over this exact topic. Remember, we poured two solutions together, A and B, and we did 1, 2, and then tied it, and all of a sudden the solution went from a clear or maybe it was a little cloudy color and maybe a certain amount of time to very dark brown color, which intensified that the reaction had gone to completion. This was a reaction rate. Basically, we tested several things that day. We looked at temperature and how it affected the speed of the reaction. We looked at concentration. Those two things. Those are the factors we're going to talk about here, or review here, along with. And so the first, most reactions proceed faster if the concentration of one or more of the reactants is increased. Line that is, remember, concentration tells you how many solute particles are in a given volume of solution. And so the more concentrated the solution is, the more particles. Well, if there's more particles there, then they're going to be spaced closer together and they're going to collide much quicker. And so the speed is going to go up. The temperature at which the reaction occurs, the rate of a reaction as temperature is increased. This in that first day lab as well. Remember, temperature when there are two reactant solutions where they collide, collision, where the rate, particular rate, in other words, the time it took the reaction to go to completion was whatever it was. But when we then used warmer solutions, that increased dramatically. If you might remember, you pour the two together, the completion almost instantly. Some of you had difficulties. Remember, getting your timer off and on quick, you know the time. And then when we use cold solutions, we these rate of speed that it took for it to go to completion was much slower. And so again, particle speed. The faster the particle often and the source with which. Third, the presence of a catalyst. The rates in any reactions can be increased by adding a catalyst. So we talked about catalysts earlier in our study actions, and so, we're going to how catalyst acts. It lowers the activation for it requires a minimum of energy for that reaction. That is called activation energy. When you add catalyst reaction, it lowers the energy required for the reaction. Whatever energy is available to the reaction at a given time, when you add a catalyst to that, basically what the which was now is, and so the reaction is going to occur as if you would have like racing. We'll talk motivation energy later on in unit 12. The last is the or liquid reactions that involve solids often proceed faster as the surface area of solid increased. Right? So more particle contact, more collision with a larger surface. That means that we have smaller. We talked about this. So we dissolve sugar in water. So nowadays we used to have sugar cubes rather than packets of sugar granules. Put one cube was same. When you put in a cube, which is put it in your coffee, your tea, the water molecules only come in immediate contact with the outer particles of the sugar, the outer molecules of the sugar, and as they work their way to the inside, eventually dissolve. On the other hand, so think about a packet. So if I set a cube here, it's if they're packed, same mass, same quantity of sugar particles spread over a much wider area. Same thing happens when you put them in here. The collision theory, the collision means particles, of course, is increased, and thus the dissolver is much quicker. So increased surface, increased temp or energy, increased concentration, or addition to the list will all increase the speed at which the reaction. Let's reaction, in other words, determine the actual or speed of a reaction. So here we have a hypothetical reaction where reaction A forms product B. All right. The reaction rate is the measure of one of either two things. Quickly, number one is used up. How quickly is produced. All right. So A is the reactant and B is the product. You could determine the rate of this reaction by either how quickly A is assumed or used up, how quickly B is assumed. So let's start out with moles of A and moles of B initially. Then as time for A will decrease, right? And the number of moles of B. This is the very important concept in kinetics. Right? So that reactants decrease over time used up. We say that reactants disappear. They're constants, and I use brackets here. Brackets concentration polarity. All right, so their concentration decrease over time. All right. On the other hand, and we designate that way as their concentrations are going to increase. And so we put a positive sign or just leave it positive in that regard. So uh, negative and product rates are positive. They fact right here that reactions going down and products concentration are going up or in. So as we go to the next year, of appearance, all right, rate of appearance. Remember, concentrations increase. That rate of appearance of B is equal to the change in B the time that it is passed. All right. Positive change. You're going to have more than you have final minus initial positive. Of A, again, reactants disappear. That's why we call it a rate of disappearance negative. Uh, the rate of A, rate of disappearance of A, is moles of A over delta. That change would be negative. Be negative. So the negative sign here in the equation give us a positive value for the rate. Give us a positive value. So in other words, whether they be a appearance or a disappearance are always going to be positive. So the rates are absolute value. Okay, the rates are absolute value. Now, this particular action, remember this was just A and B. The mole ratio between A and B is 1 to 1. Because of the 1-to-1 mole ratio, reaction, the rate of disappearance of A will equal the rate of appearance. Remember, note the negative sign for disappearance of a reactant. So the values of two rates equal because the mole ratio between the two is 1 to 1. If it is not 1 to 1, that's not true. Right? In stoichiometry, mole ratio plays a critical role in the reactants or the production of products, and that same effect is seen here in regard to reaction speed. So reaction rates in terms of concentration. Okay. Most chemical reaction rates are measured in terms of the change in concentration divided by rapidly the change. All right. So what we're here appearance that would be equal to the change in concentration. Remember, change in concentration over the change in time. Just remember, change in anything, whether it be rate, moles, what temperature, volume, or whatever. Remember, is the final condition value minus the initial. So just like all, this be the concentration, and its initial condition divided by delta T is the same thing. T the initial. Normally, at time as an initial, in other words, we hit when we begin to react. Inside is zero. It doesn't have to be, but normally it is. And so TF minus TI or delta T would just be equal to TF. Actually, since we're looking at concentration, molarity, rather than change in moles most of the time, is therefore measured in molar second. Okay. All right. So here I say consider the following reaction in which butyl chloride reacts water to form all alcohols. Butyl butyl alcohol or butanol, and we point one chloride prepared in the various times after time, and we start then the following accordance. So look at the next page, this little data table here, and see what's going on. So we started here that we readings about well, here we got to 200 seconds, and then it looks like seconds until we got down to 800. And so we said that we started with a concentration of butyl chloride 0.000 mole. All right. Now we took then our first reading in 80 seconds and see has gone down. Well, that's not surprising. Remember, butyl chloride is as they are used up, disappear. So concentration. Let's take a look then at what we have right here. Okay, and over here is the rate. We're going to see that here in just a second. All right, and again, see how we then calculate. So these data can be used to calculate the rate of disappearance of butyl chloride in units of molar per second. So let's say use T equals 0 as our initial, and final is 0 seconds. So we're going to use this here as T, and this one here as T final. All right. So our rate of disappearance now is the opposite of the change in concentration of T. So we're going to use these here. So this would be the concentration minus the concentration of butyl chloride initial, okay, over T final. So our final concentration, which is this one, is 0.0, so this would be negative 0.0905. Our initial concentration 0.100, and T final is 50.0 minus 0. So we have, remember this negative sign is here. So the difference is that, all right, negative 0.0005, difference between these two. And as you can see, it should be negative. And 0.0 is 50.0. So the rate can be 269 times the negative per second, which is where that number comes from, right there. Okay. Now things to know. First of all, the concentration actually decreases. So decrease, but again, we use so that our rate is absolute value. All right. User, which then gives us a positive value for our rate. Otherwise, all these rates would be technically are negative. Times going on, concentration of ethyl chloride, the reacts less. All right, as we can see here. All right, now we won't do any more calculations with this data, but I want you to look at something. As we take more readings after more past, concentration of our react continues to decrease. Ultimately, after 10,000 seconds, it's. But notice what happens to the rate. All right. So each successive rate. So now these two here, 50 and 100. If we use that 100 as T final and T initial, these two are right here. The next two, and so on and so on. Increasing that. Think about that. Why is the rate decreasing? Because why? Because the reaction concentration is decreasing. All right. Well, what does that mean? Well, it goes right back to collision particle or collision theory. I'm sorry. If there are particles colliding, then the speed at which they collide is going down. All right. So fewer reactants. Slow speed. All right. So as the number of reactant particles continues to decrease over time, the rate of the reaction is going to decrease right along with it. Okay, it's going to decrease right with it. Again, all of these are positive, though in reality, the change in concentration is negative because we have a sign here disappearance value. Know about that. Got it. The calculated average rate for each time is shown in the third column. Each successive times gives us each then successive rate as we go along. Right. Makes sense too. Let's go to the next thing. Let's look at reaction rates and stoichiometry. Reaction rates are based on mole ratio, just like anything else regarding action quantity. It's all based on mole ratio, right? So here we have a general here. A plus B looks like a D placement. The lowercase a, b, c are the mole coefficients used to balance the equation. The rate for this is given by actually of of these expressions. All right. Notice that A and B have a negative sign in front of them. All right. Remember, A and B are reacting and they disappear. All right. They disappear. And so we have a negative sign in front of the rate so that the rate comes out to be absolute value. All right. C and D are the products. That's negative. Product up here. Remember, that's functions are increasing with time. The exact of this. And so as you can see here, there is no negative sign in front of either of these. Right? You may set any two expressions equal to one another in order to calculate the rate of disappearance of any of the reactants or products. Basically, setting up a proportion. The mole ratios to the coefficients of the reaction. Right? So, the rate of A, which is negative 1 over the 1 of A, change over A. If we set the rate of distance between A and B, I set up action right here. Both of these show the rate of the particular reaction. We set them equal to each other. You can see the independent mole coefficient numbers. We want to compare disappearing with the rate of appearance of P. We would set these two one another. All right. With use these two and set up our proportion. And so they're directly proportional to mole coefficient. Mole coefficient number is the change in the rate is bigger right along with it. All right, and vice versa. So next page here. Like I said, you set calculate the or disappearing reactants. For example, if you wanted to compare to the rate of appearance of D, all right? So the rate of disappearance of A was 1 over A times the change in concentration of A. The rate of appearance now this because D is over D, the mole number, change in concentration of D over delta T. One thing, so this would be the expression we use. Now I want you to know, right? Delta T and the T must be the same. In other words, we have to check have the same quantity of time as passed. So those delta T's are always going to be equal. And so the delta T's will cancel. And like that. So 1 times the change in concentration of A over A equals 1 over D times the change in concentration of D. And so that would be a simplified way of writing rate expression. They are both correct. All right, they're both correct. This, of course, is a little has been simplified. You may do that each and every time. Every time you compare the rate of appearance of your reactants or the rate of appearance of your reactants, the appearance of your products, the amount of time this passes in case passes equal. So you're comparing apples to apples. To compare the rate of disappearance of B, the rate of appearance of C. All right, this disappearance change in concentration T over delta T equals 1 over C. Change in concentration T over T is the full weight, right? Again, cancel out and write it in the more simple way of 1 over V, change in concentration of V is 1 over V, the change of C. Either way is fine. Okay? Either way. You can save yourself a little guess and eliminate. All right, so let's do a couple of things here. So here we have a reaction oxygen from ozone. Ozone, I think we talked about the ozone layer earlier this semester. The ozone layer is kind of a UV protective layer of reaches of the atmosphere that helps us absorb a lot of ultraviolet light that comes from the sun before it strikes the earth. And so that's what the ozone layer is up there for. As ozone is broken down in excess of ultraviolet light, or by adding chlorofluorocarbons to the atmosphere. Talk about that. That's a catalyst reaction too, which is why we banned CFCs about 20 years ago. You get formation of oxygen, which is not a thing, but when you're thinning the ozone layer, you're thinning out that protector that excessive ultraviolet light. Anyway, here's the reaction. Two ozone react. The question is, how is the rate of disappearance of the rate of appearance of oxygen in the precious? All right. So I'll write out both ways, long way and short. So one is a reactant, so that's a rate of disappearance. So -1 over our mole number, which is 2 now. All right, -1 over 2 times the change in ozone concentration over change in time equal to this is appearance now. Our products appear, so this would be positive. 1 over 3 is our mole now. Our mole ratio is 2 to 3 times the change in O2 over change in time. So that is a perfectly acceptable rate expression for this. Like I said, we could simplify it. We could do that. We could eliminate the T's. Okay, we could eliminate the delta T's. And so in doing that, now this is 1/2, really need there. We eliminate that too, because 1 times that is just the same as that. And so what we end up with then is change ozone concentration negative now over 2 equals the change in oxygen concentration over 3. So here would be a simplified version of this. Again, the ones could be left here just like we did in the equals to be eliminated. So that's a way of setting it even a little further. Either one of these is perfect. Okay. So that is the rate for this reaction. The second example for this same reaction, if the oxygen is 6.0 times 10 to the -5 molarity per second, that particular instant, what is the value of the appearance of ozone at this same time? Okay, so now we're going to use our reaction and actually calculate rate. All right. I'm just going to rewrite the rate expression. I'm going to use So we have change of concentration over 2. Let's remember its mole mass 2 is equal to the oxygen concentration over, which is the mole coefficient for oxygen. So now I'm going to plug the numbers in. So the change then in the ozone concentration over 2 is equal to, we have so ratio, it's a direct relationship. In any direct relationship, remember, we cross it by. So let's just do that. So we have 2 times 6.0 times 10 to the minus 5th equals, now this is negative 3, so this is negative 3 times the change in our ozone concentration. All right? So we will divide both sides by negative 3. That, of course, cancels. And the change in ozone concentration then would be 2 times 6.0 times 10 to the minus 5th divided by 3. And of course, it is negative because ozone is a reactant. It is a rate of disappearance, which means it actually has a negative value. And to 2 sig figs, which is what we have right here, that's all we got, is negative 4.0 times 10 to the minus 5th molarity per second. All right? Let's take a look at that and make sure that makes sense. The rate of disappearance is less, of course, is less rate of appearance of oxygen. In fact, it's by a value of 2. We'll take a look at the ratio of the reaction 2 to 3. All right, ozone 2 to 3. The rate of ozone disappearance to oxygen appearance is also 2. So it's absolutely imperative for rates involving geometry that you have a correctly balanced equation in order to and thus a rate. Okay, so these are questions. These give us a rate of reaction based on speed of reaction and geometry of the so you should be able to complete the rate of the Kinetics assignment number 1 for unit 1, and then also the reaction or rates assignment. So those 2 assignments you should be able to complete after viewing this lesson. So this is Mr. I'm signing off. Again next time, start talking about rate loss. Okay. Up here, there I am. I say bye for now, everybody. Here. And I miss you guys as I always do. Every time I'm here, I miss each class out there as you normally would be. Again, I hope with all that these video lessons make you feel like that we're getting the words like we do. So this is me signing off till next time. Everything.